Okay, class. So last time, in the first part of the lecture, we discussed um, one of the idea to design the filter to satisfy some of the specifications. So we start with the frequency response function and visualize it by viewing all the terms involved in the calculation of the magnitude as the length of the vectors from a certain point on the j omega axis, the imagined axis, to the poles and zeros involved in the transfer function. So for instance, when we look at the low-pass filter, it's usually accomplished by fixing some of the poles around this region in the complex plane surrounding the origin. And this enables the effect that in the low frequency range, the distance from the poles to the point in the geometric axis are relatively short. And since those terms will enter the transfer function in the denominator, smaller denominator will indicate that the magnitude will be relatively large. On the other hand, when we move the frequency towards infinity, meaning we have higher frequency, the vectors indicated by these red arrows in this figure are longer. And once they become longer, as they enter the calculation in the denominator, the resulting magnitude will become small. And as a result, we end up with a low-pass filter. And in the next section, we'll give an example to illustrate this particular effect, how to arrange, position those poles, and how to achieve this, how to do calculations, and so on. Okay. Now, if we want to do a bandpass filter, one way to accomplish that, so before doing that, let me mention that in this case, we assume that there are no zeros, only poles. Now, if we want to design a bandpass filter, one way to accomplish that is first of all, figure out what will be the frequency range that you do not want. So you want the passband to be surrounded by. Right? So let's say we want the passband or bandpass filter to be around omega naught. That one way to do that is to select your poles around the frequency. And of course, if a pole is complex, its complex conjugate has to appear as a characteristic root as well. So that's why I draw these in a symmetric manner. And in this way, right, if your frequency is near omega naught, of course, you have to connect everything to that. And draw this more like straight lines. Although you will have a few of them that appear to be long vectors, these short ones will become a dominant factor when we actually put them into calculation. These type of arrangements is usually called wall-to-wall poles. And by putting everything into calculation, we'll be able to find out that the magnitude response function will behave in this manner. That reaches the maximum at omega equal to omega naught and becomes smaller when you move the frequency away from there. And the more poles you place to it, the thinner this curve will become. This is a way to design to design a bandpass filter using this wall-to-wall pole arrangement. What about band stop filter? Right? In the previous two examples, we assume there are no zeros involved. When you design a band stop filter, meaning with some particular frequency you don't want anything to go through, some zero will be involved. And again, let's say for the band stop filter, you found out that omega naught is the frequency you don't want anything to pass through, right? And one way to do that is to have two zeros placed at this frequency in the stop band, right? So we use this to represent the circle represents zeros. Zeros means the roots of the polynomial in the numerator of your transfer function. And we use the cross to represent poles. Right? And one commonly used band stop filter, goes like this. We have two zeros selected on the geometric axis. And we're going to choose a pair of poles on the same semicircle. Of course, they're complex conjugate, and the parameter to be played with will be this angle theta. Right, so in this case, we know for this arrangement, the zeros are plus minus j omega naught, since they're on the geometric axis, and the poles they're on the same semicircle, so omega naught, times e to the plus minus j pi minus theta will be the angle of the two poles. And I enter these poles as zeros in the transfer function. It's not difficult to find out that h of s will be, numerator is s squared plus omega naught squared, so that you have two roots that are the two zeros plus minus j omega naught. And I place the two poles in the denominator polynomial, you will have s squared plus 2 omega naught cosine theta times s plus omega naught squared. Okay. So if we arrange the poles in zero in this manner, we end up with this transfer function. And using that, we can easily draw the frequency response function. And the magnitude in this case look like this. Now, since omega naught j omega naught is selected as a zero, so the frequency response function has to be zero at this point. No matter how you choose that parameter theta, you have to have a zero here, right? And it's easy to find out when you choose at the origin, the DC gain of this transfer function, that's 1 omega equals 0, is the constant term in the polynomial divided by the polynomial, the constant term in the denominator of polynomial, and it should be 1. When omega is really high, it's high frequency, right? So the quadratic term should become dominant, and you end up with having these two terms, and since they have both coefficients equal to 1, when omega is really high, the magnitude is also close to 1. That in the middle usually look like this, on one side, and this on the other side. And when you choose this theta close to 90 degrees, meaning when you move your pole close to 0, the more you do that, you see this drop and rise in the magnitude response function more steep, right? And this curve here is theta farther away from 90 degrees. And this is usually useful when you have a particular frequency that you want to completely filter it out from your signal. For instance, as we mentioned, maybe you want to have this 60 hertz or 50 hertz AC noise removed from the signal you receive. So this could be the one to use. However, it should be noted that when your poles and zeros are close together, this may lead to a number of other issues. For instance, stability, and the way to select the parameters, and can render other potential issues as well. So this really a trade-off how you can uh, select the parameters in a practical scenario. Now this type of filter is called a notch filter. Of course, you see there's a notch in this in the shape of the magnitude response function. And of course, in terms of this, the type of filter is a type of band stop filter. Okay.